Start the read of Chapter 3, Section 3, the third law of motion. Newton's third law. Push against the wall and what happens? If the wall is sturdy enough, usually nothing happens. If you pushed against the wall while wearing roller skates, you'd go rolling backwards. Your action on the wall produced a reaction, movement backwards. This is a demonstration of Newton's third law of motion. Newton's third law of motion describes action-reaction pairs this way. When one object exerts a force on a second object, the second one exerts a force on the first that is equal in strength and opposite in direction. Another way to say this is to every action force, there's an equal and opposite reaction force. Action and reaction. When a force is applied in nature, a reaction force occurs at the same time. When you jump on a trampoline, for example, you exert a downward force on the trampoline. Simultaneously, the trampoline exerts an equal force upward, sending you high into the air. Action and reaction forces are acting on the two skaters in Figure 21. The male skater is pulling upward on the female skater, while the female skater is pulling downward on the male skater. The two forces are equal, but in opposite directions. Action and reaction forces don't cancel. If action and reaction forces are equal, you might wonder how some things ever happen. For example, how does a swimmer move through the water in a pool if each time she pushes on the water pushes back on her? According to the third law of motion, action and reaction forces act on different objects. Thus, even though the forces are equal, they're not balanced because they act on different objects. In the case of the swimmer, as she acts on the water, the reaction of the water pushes her forward. Thus, a net force or unbalanced force acts on her, so a change in her motion occurs. As the swimmer moves forward in the water, how does she make the water move? The reading checks ask, why don't action and reaction forces cancel? According to the third law of motion, action and reaction forces act on different objects. They don't cancel, they just act on different objects. Rocket propulsion. Suppose you're standing on skates holding a softball. You exert a force on the softball when you throw the softball. According to Newton's third law, the softball exerts a force. This force pushes you in the direction opposite the softball's motion. Rockets use the same principle to move even in the vacuum of outer space. In the rocket engine, burning fuel produces hot gases. The rocket engine exerts a force on these gases and causes them to escape out the back of the rocket. By Newton's third law, the gases exert a force on the rocket and push it forward. The car in Figure 22 uses a rocket engine to propel it forward. Figure 23 shows how rockets were used to travel to the moon. Visualizing rocket motion. Figure 23. On the afternoon of July 16, 1969, Apollo 11 lifted off from Cape Kennedy, Florida, bound for the moon. 8 days later, the spacecraft returned to Earth, splashing down safely in the Pacific Ocean. The motion of the spacecraft to the moon and back is governed by Newton's laws of motion. Apollo 11 roars towards the moon. At launch, the rocket's engines must produce enough force and acceleration to overcome the pull of Earth's gravity. A rocket's liftoff is an illustration of Newton's third law. For every action, there is an equal and opposite reaction. As Apollo 11 rises, it burns fuel and ejects its rocket booster engines. This decreases its mass and helps Apollo move faster. This is Newton's second law in action. As mass decreases, acceleration can increase. The lunar module uses other engines to slow down and eases into a soft touchdown on the moon. A day later, the same engines lift the lunar module again into outer space. After the lunar module returns to Apollo, the rocket fires its engines to set it into motion towards Earth. The rocket then shuts off its engines, moving according to Newton's first law. As it nears Earth, the rocket accelerates at an increasing rate because of Earth's gravity. Momentum. A moving object has a property called momentum that is related to how much force is needed to change its motion. The momentum of an object is the product of its mass and velocity. Momentum is usually given the symbol P and can be calculated with the following equation. Momentum in kilogram meters per second, different from acceleration in that momentum is kilogram meters per second, equals the mass in kilograms times velocity in meters per second. Therefore, P equals mv. And yes, momentum is given the symbol P. M was taken. P equals m times v. Unit for momentum is kilogram meters per second. And just like velocity, momentum has a size and a direction, which they left off in the formula. Suppose you know the speed of an object, then the size of the momentum can be calculated by substituting the speed for the velocity in the above equation. In this example, we'll solve for momentum. At the end of a race, a sprinter with a mass of 80 kilograms has a speed of 10 meters per second. What is the sprinter's momentum? This is what you know. The mass of the sprinter equals 80 kilograms, and the velocity equals 10 meters per second. And we know that that isn't a true velocity because, once again, they didn't give us a direction. This is what you need to find, momentum, expressed with the unit P. P equals mv. Momentum equals mass times velocity, or in this case, speed. Substitute in the values, 80 times 10 equals 800. And the units again, 800 kilogram meters per second. The sprinter's momentum is 800 kilogram meters per second. This time you need to take out a piece of paper. You can use the back of your note-taking guide to answer these 4 problems, the 4 practice problems. Force and changing momentum. If you catch a baseball, your hand might sting, even if you use a baseball glove. Your hand stings because the baseball exerted a force on your hand when it came to a stop, and its momentum changed. Recall that acceleration is the difference between the initial and final velocity divided by time. Also, from Newton's second law, the net force on an object equals its mass times its acceleration. By combining these two relationships, Newton's second law can be written in this way. Force equals mass times final velocity minus mass times initial velocity divided by time. In this equation, mvf, or mass times final velocity, is the final momentum, and mv1 is the initial momentum. The equation says that the net force exerted on an object can be calculated by dividing its change in momentum by the time over which the change occurs. When you catch a ball, your hand exerts a force on the ball that stops it. The force you exert on the ball equals the force the ball exerts on your hand. This force depends on the mass and initial velocity of the ball and how long it takes the ball to stop. The law of conservation of momentum. The momentum of an object doesn't change unless its mass, velocity, or both change. Momentum, however, can be transferred from one object to another. Consider the game of pool shown in figure 24. When the cue ball hits the group of balls that are motionless, the cue ball slows down and the rest of the balls begin to move. The momentum the group of balls gained is equal to the momentum that the cue ball lost. the total momentum of all the balls just before and after the collision would be the same. If no other forces act on the balls, their total momentum is conserved. It isn't lost or created. This is the law of conservation of momentum. If a group of objects exerts forces only on each other, their total momentum doesn't change. And in figure 24, momentum is transferred in collisions. At figure A or picture A, before the collision, only the cue ball has momentum. When the cue ball strikes the other balls, as in picture B, it transfers some of its momentum to them. When objects collide, collisions of two air hockey pucks are shown in figure 25. Suppose one of the pucks was moving in one direction and another struck it from behind. The first puck would continue to move in the same direction but more quickly. The second puck has given it more momentum in the same direction. What if two pucks of equal mass were moving towards each other with the same speed? They would have the same momentum but in opposite directions, so the total momentum would be zero. After the pucks collide, each would reverse direction and move with the same speed. The total momentum would be zero again. This time you need to either use the back of the note-taking guide or a separate piece of paper to answer questions 1 through 7 of section 3.